The future isn't coming, it's already here, in code and steel. First up, a disturbing innovation in digital deception. Researchers have identified the rise of deepfake as a service platforms that are revolutionizing biometric spoofing and identity fraud. How does this work? These platforms operate on subscription or pay-per-use models, offering sophisticated AI tools that can generate hyperrealistic synthetic media faces, voices, and even full body movements with minimal technical expertise required. They use generative adversarial networks, GAN, and diffusion models trained on massive datasets of human biometric data. The most advanced systems can bypass multi-factor authentication by synthesizing real-time video responses to verification challenges. Why does this matter profoundly? We're witnessing the weaponization of AI accessibility. Previously, creating convincing deepfakes required significant computational resources and machine learning expertise. Now, these platforms democratize digital deception, making sophisticated identity theft tools available to anyone with a credit card. This threatens not just individual security, but institutional trust in digital verification systems. Financial institutions, government agencies, and social platforms that rely on biometric authentication now face an arms race against increasingly accessible spoofing technology. The report suggests we're entering an era where verifying human identity may require fundamentally new approaches beyond current biometric paradigms. Speaking of AI tools, meanwhile, in finance, Wall Street professionals are revealing their favorite AI tools and applications, showing how these technologies are being integrated into high-stakes decision-making. How do these tools work? The most popular applications include natural language processing systems that analyze earnings calls and regulatory filings for sentiment and risk indicators, machine learning models that identify market microstructure patterns invisible to human analysts, and reinforcement learning algorithms that optimize trading strategies in real time. Quantitative hedge funds are deploying transformer architectures to process alternative data sources, satellite imagery, social media sentiment, supply chain logistics, converting unstructured information into predictive signals. Why does this transformation matter? We're seeing the professionalization of AI in finance move beyond experimental phases into core operational infrastructure. These tools aren't just augmenting human analysts, they're creating entirely new forms of financial intelligence. The most sophisticated systems operate with what's called explainable AI frameworks, allowing traders to understand why models make specific predictions rather than treating them as black boxes. This represents a significant evolution from earlier algorithmic trading systems. The implications extend beyond Wall Street as these tools become more accessible. They're democratizing financial analysis capabilities that were once exclusive to institutional players with massive computational resources. From digital to physical. Now to robotics. German engineers have developed a humanoid robot designed to transform factory work with unprecedented human-like dexterity and adaptability. How does this system work? The robot utilizes a combination of advanced computer vision, force-torque sensing, and reinforcement learning to perform complex manipulation tasks. Unlike traditional industrial robots that follow pre-programmed paths in controlled environments, this humanoid employs what's called imitation learning, observing human demonstrations, and generalizing those movements to novel situations. Its hands feature tactile sensors providing haptic feedback, allowing it to handle fragile objects with appropriate pressure. The locomotion system uses dynamic balancing algorithms that enable walking on uneven surfaces while carrying payloads. Why is this breakthrough significant? We're witnessing the convergence of AI cognition with physical embodiment. Previous factory robots excelled at repetitive tasks in structured environments, but struggled with variability. This humanoid represents a paradigm shift toward general-purpose robotic workers that can adapt to changing conditions without complete reprogramming. The implications extend beyond manufacturing. Similar platforms could eventually perform maintenance in hazardous environments, assist in healthcare settings, or respond to emergencies. This isn't just automation, it's the creation of embodied intelligence that can reason about physical constraints and adapt its behavior accordingly. Nature inspires innovation. Speaking of embodied intelligence, researchers have created a robotic bat that reveals how big-eared bats navigate and hunt using sophisticated echolocation. How does this biomimetic system work? The robot replicates the biological mechanisms bats use to process sound echoes for spatial navigation. It emits ultrasonic pulses through piezoelectric transducers that mimic bat vocalizations, then uses an array of microphones to capture returning echoes. The key innovation is in the signal processing. The system employs convolutional neural networks trained on real bat echolocation data to interpret complex echo patterns, distinguishing between different surfaces, objects, and even moving targets. The robot's wing design incorporates flexible membranes that can adjust shape mid-flight, allowing it to maneuver through cluttered environments. Why does this matter beyond biological research? We're seeing the emergence of what's called bio-inspired robotic systems that don't just copy nature, but understand and replicate underlying principles. This robotic bat demonstrates how biological solutions to sensory challenges can inform technological innovation. The echolocation algorithms could revolutionize autonomous navigation in environments where visual systems fail underwater, in smoke-filled buildings, or in complete darkness. More fundamentally, it shows how combining biological insights with artificial intelligence can create systems with capabilities exceeding either approach alone. This represents a new frontier in robotics, not just building machines, but engineering embodied intelligence informed by millions of years of evolutionary optimization. And finally, autonomy takes a hand. In perhaps the most startling development, engineers have created a robotic hand that can literally crawl away from its arm to manipulate objects independently. How does this disarticulated manipulation system work? The hand contains its own power source, processing unit, and actuation system, allowing it to operate autonomously once detached. It uses a combination of computer vision for target identification and reinforcement learning for locomotion planning. The crawling mechanism employs what's called peristaltic motion, sequential contraction, and expansion of segments similar to how worms move. Once at its destination, the hand can perform dexterous manipulation using its fingers, which incorporate both position and force control. The communication system uses ultra-wideband radio for coordination with the main robotic body. Why is this modular approach revolutionary? We're witnessing the decoupling of manipulation from traditional robotic architectures. Previous robotic systems treated hands as endpoints of arms, limiting their operational range. This crawling hand represents a paradigm shift toward distributed robotic systems where components can operate independently and reconfigure as needed. The implications are profound. Imagine search and rescue scenarios where robotic hands could navigate through rubble too narrow for full robots, or manufacturing environments where tools reposition themselves autonomously. This isn't just incremental improvement, it's rethinking the fundamental unit of robotic agency. We're moving from integrated systems to swarms of specialized components that can collaborate dynamically based on task requirements. Intelligence is escaping screens and taking physical form. Subscribe for tomorrow's discoveries.